In this next module, I'm going to give you some strategies for dealing with missing data. When you run a regression, like a logistic regression, it's important to realize that if an observation is missing a value for even one variable in the model, that observation will be dropped. This means that if you have a lot of variables in your model, even if each variable is just missing a handful of values, this could add up to a lot of observations being dropped. You might start with a data set of 400 observations, but your regression only includes 200. So you have to pay careful attention to missing data. How you handle missing data depends on the question you're trying to answer. For example, if you have variables that are measured with high amounts of missingness, it's advisable that you not include them in the model. But if it's your primary predictor or primary outcome or a key confounder, then dropping that variable may not be an option. Another option is to exclude observations that are missing data. If you are studying alcohol consumption and cardiovascular disease and a person doesn't have an alcohol measurement, they're not informative for your main question, so you might exclude them. You can also impute missing values, meaning that you fill in the missing data with a guess. I'll talk about that more in a minute. Certain statistical techniques also handle missing data. For longitudinal data, there are several models that incorporate more than one measurement from the same person into the likelihood function. That means if a person is missing one, but not all of their measurements, they're only going to be dropped for the measurement they missed. Finally, sometimes the missingness itself is informative. If you are doing predictive modeling, missingness might have predictive value. Most of you have probably heard of the Netflix prize. Netflix offered $1 million to the team that could come up with the best algorithm to predict a movie viewer's rating on a future movie based on their past ratings. Now, many people watch movies and don't bother to rate the movie, which means that there are going to be a lot of movies with missing values. But the fact that somebody chose not to rate the movie may mean something. People tend to rate movies that they really love or really hate. So missingness may indicate ambiguity, and that binary variable, missing or not, may have predictive value. If you decide to impute, the simplest approach is called single imputation. This is sufficient if it's just a secondary, less important variable, and if you're missing just a handful of values. You can basically plug in any value just so that the observation is not completely dumped from the model. One choice is to give everyone who has missing data the mean value for the sample. Or you can do a little better if, rather than using the mean, you use some kind of regression model to predict each individual's value based on other information you have about them. For example, I had some data on high school runners, which included their mile times. This was a variable I needed to adjust for, but it wasn't the primary predictor, and just 10 runners were missing a value. So I could have just filled in for all 10 runners the mean time, which in this case was 6 minutes and 16 seconds. Or I could even do a little bit better because I had other information that I could use to predict mile times. Some women were missing mile times, but had 5K times. I also had data on their mileage and the speed of their training. So I built regression models to predict a woman's mile time based on these other factors, and that's just a little bit less noisy than using the mean time. But single imputation has a problem. It reduces the standard deviation of the variable you're imputing, and therefore reduces standard errors and p-values. Here, I've got a simple data set where a fairly high percentage of participants are missing height. In the original data set on the left here, the mean was 67.4 inches and the standard deviation was 4.6. When I assign a value of 67.4 to everyone with missing heights, I preserve the mean, but I shrink the standard deviation to 3.9 inches. This is because I've given everybody with missing data the exact same value, so I've reduced the variability. And this is going to affect my standard errors and my p-values. So multiple imputation gets around this problem. In multiple imputation, you create multiple data sets, typically 5 or 10 data sets. Rather than just giving everyone a single height, you generate multiple heights for each person. This preserves the standard deviation. This is easier to illustrate with a picture. Here, rather than giving every person with a missing height that same value of 67.4, I randomly generated heights from a normal distribution with a mean of 67.4 and a standard deviation of 4.6. I generated 5 heights per person, so I have 5 different data sets. But notice now my standard deviation is correct. It's still 4.6 inches. Of course, this is more complicated than single imputation because now you have to run your logistic regression or whatever your regression or model is on each of the 5 data sets separately, and then you have to average the results together to come up with a single result, like a single beta. Both SAS and R have built-in algorithms that will do this for you, so it's not terribly hard, but it does add a layer of complication. So this is probably not worth doing if you just have a secondary variable with a low amount of missingness. In that case, single imputation would be just fine. Here, I've put together some guidelines for which strategy you might choose for a given study design and a given level of importance of your variable. So for example, if you are doing an observational study over here, you would likely exclude any observations that were missing data on either the primary predictor or the primary outcome. They're not going to be informative for your main question. But if someone is just missing data on a key confounder, you're likely still going to include them, but you're going to impute their value for that confounder. If there's very low missingness, single imputation is just fine. If there's more moderate to high missingness, you're probably going to want to use multiple imputation. If you're talking about longitudinal studies, as I mentioned, you can use certain types of models that will handle missing data when you're missing some of your repeated measurements. These models can handle that. And so you can use this chart and common sense to figure out the best strategy for a given situation.